Let's derive the quadratic formula. So here's the quadratic formula. It's just a formula that you can use to solve any quadratic equation. So once you have a quadratic equation, you can just take this formula and plug values directly in and get the solutions to the quadratic equation. Okay. So first, let's remind ourselves what exactly a quadratic equation is. It's an equation to where each term in the equation, or like each expression on either side of the equation, is a quadratic expression, or it's all quadratic terms. Okay, so, but now what is a quadratic expression or a quadratic term, if it's just one term? Well, that's a quadratic expression is a subset of a polynomial expression, with a polynomial expression being an expression to where all of the variables in the entire expression are strictly raised to whole number powers. So 0, 1, 2, 3, 4, any positive integer, or also 0. But if it's raised to the power 0, that's kind of like just a constant. Okay, so really like positive integer powers. Every single variable in the entire expression is raised to a positive integer power. But you can think about this with as many variables as you want, because if we had something like 3x y squared z, well, this is a polynomial term as well. But you look at this has degree, and you just add up so 1 plus 2 is 3, 3 plus 1 is 4. This is a polynomial term with degree 4. And if we keep going, is equal to, something like that. Well, this is a polynomial equation. Or if I just left the equation symbol off, this is a polynomial expression in 3 variables. And it's a polynomial expression in variables x, y, and z. Or, again, a polynomial equation in variables x, y, and z. This term has degree 4. This term has degree 3. This term has degree 4. Okay? And so a quadratic equation in any number of variables, or a quadratic expression, is going to be, it's a subset of polynomial equations to where every single term is obviously a polynomial term of degree 2 or lower, where at least one of the terms is of degree 2, otherwise then it would just be linear. So at least one of the terms needs to be of degree 2 so it could be quadratic. So none of these terms here are quadratic, right? They're all greater than degree 2, but note that like this, you might say, well, this is linear. They're all degree 1. Well, no, this term as a whole is degree 2. So this would be a quadratic term. And if you had this would be a quadratic equation in the variables x, y, and z. Okay, degree 2 term, degree 1 term, degree 2 term. Okay, and so what we want to do is derive the quadratic formula, and we're going to do it for the case of a quadratic equation in one variable, in the variable x. Okay, so the way we write this is that anytime you have a quadratic equation in one variable, okay, it could be in any form with all kind of brackets and all kind of stuff going on, but you could always expand everything out, combine all the like terms, and you could put any quadratic equation into this form, right? If you have a quadratic equation, with no matter what it looks like initially, it could have stuff going on all over the place. You could expand everything out, combine like terms, distribute, bring everything to one side, and put it into this form, where a, b, and c are any real numbers, except a can't be 0 because then it's not quadratic anymore. But b and c can be any real numbers. We're just thinking about real numbers. The quadratic formula is not that we can't have, we can see that we'll be able to have actually imaginary solutions. However, the quadratic equation is such that we're not going to have non-real coefficients. But you can still have a quadratic equation. A could potentially be any complex number. B could be any complex number. C could be a complex number. But the quadratic formula is for the case where you've got this here, where A, B, and C are real, pure real coefficients. Okay. Now, before we go ahead and derive the quadratic formula, just note that I've been mentioning this as we've gone through this chapter, that when it comes to, so you might think, well, okay, to solve a quadratic equation in multiple variables is going to be so much different. Not at all. So these literal equations, these equations with multiple variables, it would be the same process. So if we were solving a quadratic equation in like 3 variables, x, y, and z, well, we're going to be solving for one of the variables. That's the idea. That's how you always solve an equation with multiple variables. You choose one of the variables to solve for. And when you do that, it's kind of like you're treating all of the other variables that aren't the main variable like they're constants. That's how you kind of look at it. And so in that case, we would put it, what would happen is like A would be some expression of the other variables. B would be some expression of the other variables. C would be some expression of the other variables in constants. And so you could still apply the quadratic formula in that case. So yes, we're just doing this for a single variable here, a quadratic equation, a single variable, but going any of the equations we learn how to solve in this entire chapter easily extend to multiple variables, right? Like, okay, let's solve a linear equation in 5 variables. So 3x minus 2y plus z is equal to k plus w. Let's solve for x. We're about to solve a linear equation in 5 variables. Okay, let's add 2y to both sides and subtract z from both sides. Okay, let's divide both sides by 3. There you go. We just solved a linear equation in 5 variables. Now it's a lot more messy. It looks a lot. It's a lot more. You know, it's not as clean and concise, but it's the same idea. There's no, just because you're extending the equation to multiple variables doesn't change anything. It's the same idea here. Okay. So now, how can we derive a formula for the solutions of x here to this equation, this general quadratic equation? How can we derive a formula for what x is equal to, the solutions of x? Well, we can use the completing the square process. Like there was 2 methods we learned outside of the quadratic formula to solve quadratic equations. We learned the zero product property, the factoring method, but we also learned the completing the square method. So let's complete the square here. It's just going to be a little challenging because we have to keep track of all these variables, but we can still do this, no problem. So let's go ahead and solve this with completing the square. So what we do is notice that a, b, and c could be positive or negative, right? You take any 3x squared minus 2x plus 5, right? So a is 3, b is minus 2, c is 5. So we're going to try and keep track of the signs here. We're going to honor this original form here, ax squared plus bx plus c, which allows for a, b, and c to be negative. That's fine. So, okay, ax squared plus bx, if we subtract c from both sides, we get 0 minus c over here. And then let's put the plus, and now we have this spot here. We need to create a perfect square trinomial. Okay, so now we saw that. This gets kind of confusing because I don't want to say x plus a. Let's do x plus d, since we're not using a d in here. So x plus d squared is, we know, is x squared plus 2dx plus d squared, right? So we want to find out what d is, as if we want to make a perfect square trinomial here. So we can see that. Well, no, okay, we can't do this yet. We need to first divide through by a. So, right now this is, I don't want to confuse you. This is what we have at the moment. We just subtracted c from both sides. Now we need to get a coefficient of 1 in front of the leading term. So we've got x squared plus b over ax is equal to minus c over a. Okay, now there we go. So now we see that to create let me leave some room here, to create that perfect square trinomial. Okay, we can see that 2d needs to be equal to b over a, right? So d needs to be equal to b over 2a. So d squared then is b squared over 4a squared. And then we want to add that to both sides. Okay, and so with that, we know we have this perfect square trinomial, so we know we can write that as x plus b over 2a squared, right? So, okay, now let's go ahead and simplify this a little bit. So we can multiply this by 4 over 4, this first term, so minus 4c over 4, and then multiply by 4a over 4a. So minus 4ac over 4a squared plus b squared over 4a squared. So which is b squared minus 4ac over 4a squared. Okay, so let's write that. Here we've got b squared minus 4ac over 4a squared. Okay, now square root property, plus or minus. Okay, so we've got, let's see, x plus b over 2a is equal to, then we can do, so plus or minus, so we've got the square root of b squared minus 4ac, and then the square root of 4a squared. Okay, x plus b over 2a is equal to, so we've got, let's see, plus or minus b squared minus the principal square root of b squared minus 4ac all over, and then this is going to be 2a down here. Okay, so now let's subtract b over 2a from both sides, so plus or minus and there we go. So we can combine these fractions. We've got minus b plus or minus principal square root of b squared minus 4ac over 2a, and there we go. That's the quadratic formula. So if you ever have a quadratic equation, you can expand everything out, combine like terms, put everything on one side, get it into this form. Again, b can be 0, c could be 0, but just a can't be. And then just plug those coefficients into this formula. And you're either going to have, most of the time you'll have two solutions because this plus or minus here, but sometimes you might have one solution. If this turns out to be b squared minus 4ac is 0, you might have one solution. If it's positive, you'll have two real solutions. B squared minus 4ac, that's the discriminant. If b squared minus 4ac is negative, you'll have two non-real solutions.